Today I am going to discuss Class 11 Semester 2 Physics Chapter 1 Gravitation. So let us start with a question. Why planets revolve around stars? Not only planets revolve around stars, but the stars also revolve around the galaxies. Every body in this universe is under a force field, and this force is gravitational force. Now move on. We study Newton's law of gravitation. We consider two masses, capital M and small m. One of them is larger mass and one is smaller. Their distance are apart. Now Newton's gravitational law states the magnitude of the force is proportional to the product of the masses and inversely proportional to the square of the distance between them. If the masses increases, the gravitational force of attraction increases, and if the distance between the bodies decreases, the gravitational force of attraction increases, as it is inversely proportional to the square of the distance. Now in this universe, every body feels gravitational interaction, and this gravitational interaction is always attractive in nature. Now we write the gravitational force F equals to G capital M small m by r square. This capital G is called universal gravitational constant. So Newton's law reads, every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. The universal gravitational constant G has a value 6.6743 into 10 to the power minus 11 meter cube kg inverse second to the power minus 2. Now move on. We study gravitational force in vector form. We draw the 3D coordinate system. We take two masses m1 and m2. Now m1 has position vector r1 with respect to the origin and m2 has position vector r2. Now relative distance between m1 and m2 is r21. r21 is r2 minus r1. So the force on mass m1 due to mass m2, we write F21 equals to G m2 m1 by r21 mod square r21 cap. Now the direction of this force is from this direction because r21 has the direction from m1 to m2, and we can write F21 equals to A minus F12. The magnitude of this force is same but direction is opposite. Now we study intensity of gravitational field. We take a large mass m. It has field all over direction. We take a unit mass at a distance r to test its field. Now the unit mass will experience gravitational force small f equals to G capital M into 1 by r square. Now this is the field experienced by any mass at any distance, and we write this F equals to capital G capital M by r square. This is the expression for gravitational field due to mass capital M. Now how a object experiences gravitational field when it passes through it. You see, the comet comes, when it comes close to the earth, it changes its trajectory due to earth's gravitational field. And we see in universe, every body, every masses present experience gravitational potential of everyone. A larger mass has larger potential and a smaller mass has smaller potential. Now, the expression for gravitational potential due to mass capital M at a distance r is V equals to minus G capital M by R. And gravitational potential energy at position is U equals to minus G capital M small m by small r. Now here is a picture. The earth has a gravitational potential energy as it revolves around the sun. Now we study the acceleration due to gravity. When a body moves away from the earth, it experiences acceleration due to gravity, and when a body falls on earth's surface, it also experiences acceleration due to gravity. We find this value at a height h above earth's surface. We draw the earth. It has a radius capital R and mass capital M. G is the gravitational constant. From the earth's surface at height h, we want to calculate the acceleration due to gravity. Now we consider this height h is less than the radius of the earth, and at height h the acceleration due to gravity we denote it by gh, and at earth's surface the acceleration due to gravity is g. Now there is the calculation. At earth's surface g has value g equals to capital G capital M by r square, and at height h gh is equals to, we replace r by r plus h, and we get gh equals to capital G capital M by r plus h whole square, and the ratio gh by g equals to g capital M by r plus h whole square into, this will be in reverse, r square by gm, and we get gh equals to r square by r square into 1 plus h by r whole square into g. Now this will removed, and we get a final expression for gh equals to 1 plus h by r to the power minus 2 into g for h less than r. Now we will evaluate 1 plus h by r to the power minus 2. We will expand it binomially and use this formula 1 plus x to the power minus n. Here x is h by r. So let us take a numerical example. We go to a hill which has a height from sea level 6.4 km, and radius of the earth is 6400 km. So h by r equals to 6.4 by 6400 equals to 1 by 1000 equals to 0.001. Now what will be the value of h by r whole square? This will be equal to 0.501, and h by r cube equals to 0.36881, and so on. And we see this value is gradually decreasing. So if we add or subtract 0.00001 with any number, the changes will be insignificant. This is a very smaller number, and cube is too much smaller than this. So we neglect h by r higher powers. So that is why this expression is written gh equals to g 1 minus 2h by r. Only first term is written here. So this is the expression of acceleration due to gravity at height h, and we see this that it gradually decreases with height h above earth's surface. Now we will find acceleration due to gravity at depth d below the earth's surface. Before that, we will find what is the gravitational force inside a spherical shell. Now this red colored portion is the spherical shell, and this is distance d. This shell of width d will have zero net gravitational field inside this shell, and the only gravitational force will play due to this blue colored mass, and in this surface the acceleration due to gravity is g suffix d, or we say at depth d from Earth's surface the acceleration due to gravity is gd. This is the radius of the Earth, and the remaining smaller volume is r minus d. Now this sphere r minus d will have impact on gravitational acceleration at that point, and this calculation we assume that the Earth to be a homogeneous uniform sphere of radius r, mass m, and of uniform density rho. Then we get g equals to capital G capital M by r square. We replace capital M by 4/3 pi r cube into rho, and we get a simplified expression 4/3 pi rho g r. Now at depth d we replace r by r minus d. So we get acceleration due to gravity at depth d is equals to gd equals to 4/3 pi rho r minus d into g, and we write gd by g equals to 4/3 pi rho r minus d into g by 4/3 pi rho gr, and in simplified form we get r minus d by r, or gd equals to g into 1 minus d by r. This is the expression for acceleration due to gravity at depth d, and we see this acceleration due to gravity at depth d is smaller than the acceleration due to gravity at Earth's surface. So we have derived two equations, one for acceleration due to gravity at height h above Earth's surface, which was g h equals to g into 1 minus 2h by r, and we find acceleration due to gravity at depth d below Earth's surface, gd equals to g into 1 minus small d by r, and this g decreases with depth. At the center it becomes 0. Now this variation of acceleration due to gravity with distance from the center of the Earth, we find maximum acceleration due to gravity at Earth's surface when radius is r, and below that Earth's surface acceleration due to gravity decreases with increasing r, and within Earth's surface acceleration due to gravity decreases with depth, and it becomes 0 at the center. Now we study Kepler's law of planetary motion. First law: the orbit of a planet is an ellipse with the sun at one of the two foci. Here this ellipse has f1 and f2 two foci, and sun is placed in one of the foci, and one planet is revolving around the sun in elliptical orbit. Second law: a line segment joining a planet and the sun sweeps out equal areas during equal intervals of time. This area is equal because in time delta t, the planet moves from this position to this position, and it crosses this area, and with the same interval of time delta t, this planet starts from this position and goes to this position, and this area is traversed by that planet. The Kepler's second law tells that these two area is equal, and that means the aerial velocity is the velocity, the area covered by the planet at a fixed interval of time, and it is equal. So we write dA dt equals to constant, অর্থাৎ the line segment joining planet and the sun sweeps out equal areas during equal intervals of time. And Kepler's third law, the square of a planet's orbital period t is proportional to the cube of the length of the semi-major axis a of its orbit. So what is the semi-major axis? The major axis, this is the a semi-major axis, and this is the time period that the planet revolves around this orbit. Then t square is proportional to a cube. This is the third law of Kepler's planetary motion.